In question 1A, we have a figure showing a 0.41 kilogram block sliding from A to B along a frictionless surface. When the block reaches B, it continues to slide along the horizontal surface BC where kinetic frictional force acts. As a result, the block slows down, coming to rest at C. The kinetic energy of block at A is 37 joules, and the heights of A and B are 12 meters and 7.0 meters above the ground, respectively. Question 1. What is the kinetic energy of the block when it reaches B? Question 2. How much work does the kinetic friction force do during the BC segment of the trip? Okay, so this is a question coming from work, energy, and power. So without wasting any time, let's just get the data that we've been given. Okay, so we've been given the mass of the object, of the block. Say this is 0.41 kilograms. We've been given kinetic energy at A. Say this is equal to 37 joules. We've been given the height of point A. Say this is 12.0 meters, whilst we've also been given the height of point B to say this is equal to 7.0 meters. And this is also the same with point C. It's on the same level. It is also 7.0 meters like this. Okay, so there are some constants that we're going to be using, but those are already known. By now, they should be on your fingertips. We have gravity, the acceleration due to gravity. That one you surely shouldn't forget. And the formula. So how are we going to calculate the kinetic energy of this object when it reaches point B? So since there's height being involved in this case, we are going to use what we call the conservation of energy, which states to say the mechanical energy along a segment or along a certain movement is constant unless an external force is applied. So what do we mean? That means we have mechanical energy at point 1 should be equal to mechanical energy at point 2. And what makes up mechanical energy? It's kinetic energy at point A plus gravitational potential energy at point A. This should be equal to kinetic energy at point B plus gravitational potential energy at point B. So we know the formulas of these guys, and we've already been given this guy to say kinetic energy at point A is equal to 37.0 joules. So what are we going to do? We're just going to get these guys and plug them into this formula in order for us to calculate the kinetic energy at point B. So what are we going to do? We're going to say 37. Let me just create a quick demarcation here. Okay, so what do we have? We have 37 joules plus the formula for gravitational potential energy is mgh at point A. This should be equal to kinetic energy at point B plus mgh at point B. Okay, so I'm having 37 plus the mass, which is 0.41, multiplied by the gravity, which is 9.8, like this, multiplied by the height of point A, which is 12 in this case. And this is equal to kinetic energy at point B plus mass, which is 0.41, multiplied by gravity, which is 9.8, multiplied by the height of point B, which is in this case 7 meters, like that. Okay, so I have 37 plus, I punch those guys into my calculator. I'm getting plus 48.216. This will be equal to kinetic energy at point B plus I punch again. 28.126. Okay, so this is the simplified version of the equations that I have on top. I'm going to scroll down a bit. So I'll say this guy is going to cross to the other side of the equation. Hence, I'm going to have 37 plus 48.281. For 37 plus 48.216. This is 85.216 minus 28.126. This will be equal to kinetic energy at point B. So here, I'm going to say kinetic energy at point B will be equal to 85.216 minus 28.216. I'm getting kinetic energy at point B, which is equal to 57 joules. So the kinetic energy at point B is actually equal to 57 joules. Okay, that means we are done with question 1, and question 2 is asking to say how much work does the kinetic friction force do during the BC segment of the trip. So they've told us to say the segment B to C, there is kinetic friction that is in existence, and it is doing some work. Hence, by the time the block is reaching point C, it is coming to a stop. So what are we going to do? We're going to use the same formula for the conservation of kinetic energy, but in this case, we're going to add the work done by friction. Okay, so I've already given you the expression for the conservation of energy. So mechanical energy at the initial point should be equal to mechanical energy at the final point, like that. In this case, this is point B we're talking about, and this is point C. Okay, so we're going to say kinetic energy at point B plus potential energy at point B will be equal to kinetic energy at point C plus potential energy at point C. Now, before this block comes to a stop at point C, there's friction that is doing some work, and the work that friction is doing is negative from the energies that we initially had at point B. So what are we going to do? We're going to subtract the work done by friction from the left-hand side of our equation. So I'm going to say minus the work done by friction, and this equation is going to be equal to kinetic energy at point C plus the potential energy at point C. All right. So let's move on quickly. We plug in our values. So the kinetic energy at point B is 57. We are from calculating plus the potential energy at point B. We also calculated to say it's 28.216 minus the work done by friction. This will be equal to kinetic energy is the energy possessed by an object due to its motion, due to its velocity. And at point C, this block is coming to a stop. Hence, there is no kinetic energy. So what am I going to have? I'm going to have 0 here plus the potential energy at point C, which will be equal to mass multiplied by gravity multiplied by h. So this mass here is the same as the mass that we have been using. It's constant everywhere. The gravity is the same, and the height is 7. And remember, when calculating the potential energy at point B, we also used 7 as height, which means this gravitational potential energy at point C is the same as the gravitational potential energy that we have at point B. Hence, I'm just going to get this guy and plug him where we have here as the gravitational potential energy at point C. So I'm having 28.216 there. Okay, so my goal is to find the work done by friction. Hence, I'm going to get this guy who is a negative, take him to the right-hand side of the equation, and get this guy who is a positive, and take him to the right hand side of my equation. Or if not, I can add these guys the way they are, just like that, on the right hand side. And when I find the sum of these guys, I take them to the right hand side of my equation. So let me add these two guys here in advance. So I'll say 57 plus 28.216. I'm getting 85.216 minus the work done by friction. This will be equal to 28 28.216 like this. So I'm getting this other guy now, which is a constant. I'm taking it to the other side of the equation so that I remain with it, what I'm looking for here. So I'm going to say negative work done by friction. This work is negative since it's opposing the direction of motion and bringing this object to a stop. Will be equal to what? It will be equal to 28.216 minus 85.216. So negative work done by friction will be equal to negative 57 joules. So here it is trying to show us to say the work is negative, but we can get rid of the negative on both sides of our equation. Hence, we're going to remain with the work done by friction being equal to 57 joules like this. So this work is opposing motion. That's why we were initially finding it as a negative work, since it's opposite to the direction of motion, hence bringing block or the block to a stop. So that is all on part A of question 1. We have calculated the work done by friction, and we've also calculated the kinetic energy of this block at point B. All right, so let's move on to the next question, which is question B, which is saying use momentum conservation to determine the magnitude and direction of the final velocity of ball 1 after the collision. So there are two balls here. If you pay attention, if you notice, there are two balls. There is this one and this one, which is moving here. These guys are colliding at the center there. Then they are moving in different directions. There is this one going in that direction, which is in this case ball 1, and the ball 2 here, which is going in that direction, which is at an angle of 35.0 degrees below the positive x-axis, whilst ball 1 is going at an angle theta above the positive x-axis with a velocity that is unknown yet. So what I was supposed to do was supposed to find the magnitude, which is the value of this velocity and this theta after the collision has taken place. So since this is momentum, or this is collision in 2 dimensions, we are going to take note of both the x and the y components. We already did vectors, so we're going to use both the x and the y components of the velocities, the initial velocities and the final velocities, in order for us to find the velocity of ball 1 and its direction with ease. So let's go to our blank board. We've already been given the data. Let's go to our blank board. Okay, so this is question B. Okay, so we have ball 1. So I can put up a graphic, or not a graphic, but like a simple free body diagram for ball number 1 here with its final velocity. So we have velocity directed at that angle, which is theta, and this is the v final of ball 1. So this is what we are looking for, the theta and the final velocity that is there. So if we have looked, we are going to use, or since I've already said, say this is collision in 2 dimensions, we're going to use momentum, the conservation of momentum, to say initial momentum should be equal to what? Should be equal to final momentum. So what are we having now? we're going to notice that we have momentum in the x and the momentum in the y. So we are going to deal with those momentums individually. Those in the x and those in the y, are going to deal with them differently. So I can start with before collision, which is the initial one. Before collision, we have initial momentum in the x, and we also have initial momentum in the y. So this will be equal to what? We have m1 v1 initial in the x plus m2 v2 initial in the x. This is the initial momentum in the x. So what are we going to notice? If we look at this, or let me put is equal, we have the mass of one here. Okay, here we've already been given the masses of one and the velocity, the initial velocity of one, and also the mass of two and the initial velocity of two. So if I look at my ball number one here, I can tell to say it is moving at this angle, which is 50 degrees from the positive y-axis, and it is in the second quadrant. So since the y-axis is the one which is adjacent to the direction of this velocity, which means the y component is the one which is going to carry a cos. And the x is in that direction. It is away from the theta, which is the 50 there. That means it is going to carry a sine. That means the initial velocity of ball number one in y will be equal to the initial velocity sine 50 degrees. So that's what I'm going to put there as my initial velocity. Okay, so I have initial velocity is equal to what? It is equal to sine, or initial velocity sine 50. So I'm going to say my initial momentum in the x will be equal to mass number one multiplied by velocity number one sine 50. This is the initial velocity plus the mass number two multiplied by the velocity or the initial velocity of ball number two. So the initial velocity of ball number two, I'll just get it like that since it's only existing in the x-axis and it is pointing towards the positive direction. So this is the equation that we're going to use in order for us to find the initial momentum in the x-axis. So this is going to be equal to what? I'm going to say the mass of one, of which this is 0.50 multiplied by the v initial, which is 0.900, and this multiplied by sine 50 like this, plus the mass of 2, which is 0.260 multiplied by the velocity of 2 in the x-axis, which is 0.540. Okay, like this. So I'll say this is equal to, let me just punch these on my calculator. I have 0.150 multiplied by 0.9 multiplied by sine 50. Okay, and that I'm adding 0.260 multiplied by 0.540. And what am I getting here? I'm getting 0.244 kg meter per second. So this is the initial momentum in the x-axis. I have this guy as my initial momentum in the x-axis. Now, what do? Let's go to our initial momentum in the y-axis using the same. But remember, we are only changing the initial velocity in the x-axis the y-axis for ball number 1. So P initial in the y will be equal to what? It will be equal to mass of 1 V initial of 1 in the y-axis plus mass of 2 multiplied by the V initial of 2 in the y-axis. Okay, so what do we have? We have our mass of 1, which is 0.15 multiplied by the initial velocity in the y. We said this is going to be equal to 0.900 cos 50. Since the y-axis is adjacent to the theta in our diagram, it is going to give us this. Then plus, we have mass number 2, or the mass of ball 2, which is 0.260 multiplied by the initial velocity of 2 in the y. And that initial velocity of 2 in the y-axis doesn't exist, since the velocity of 2 is initially directed along the x-axis. So this is multiplied by 0 meters per second. So the P initial in the y, initial momentum in the y, will be equal to 0.150 multiplied by 0.900 cos 50, and that should give us the initial momentum in the y-axis, which is equal to negative 0.087 kg meter per second, like this. So this is the initial momentum of the two balls in the y-axis. And why is this momentum negative? It's because the direction of the velocity in the y-axis is towards the negative y-axis. Hence, we're having negative direction or negative sign on our initial momentum in the y-axis. Okay, so now that we've calculated or we've found the initial momentums both in the x and the y-axis, what are we going to do? We are going to go to momentum after collision. I even write here to say after collision. Okay, after collision like that, we have the x component as usual. So initial momentum in the x, or final momentum in the x rather, P final in the x will be equal to what? It will be equal to mass of 1 multiplied by the V final of 1 in the x plus mass of 2 multiplied by the V final of 2 in the x, like that. Okay, so if we look at our diagram again on the final side, we can tell that this is the data that we have on mass number 1 here, whilst we also have these guys on our mass number 2. So we've been given the final velocity of ball number 2 and its direction below the positive x-axis, whilst we are looking for this guy. So we'll plug in what we have into that equation, and we are going to have the mass of 1, which is 0.150 multiplied by the V final, and since in the x is the one which is adjacent to the theta, it is going to be V final in the x cos theta. We don't know the theta as of yet, plus the mass of 2, which is 0.9 or 0.260 rather, 0.260 multiplied by the final velocity of V in the x, which is 0.7 cos. Since it is at the x component is the one which is adjacent to the theta that we've been given, it is going to carry a cos 35 like this. Okay. So that is what we have there. And we can just leave it here since it can't really go anywhere unless we just find the actual digit of this one. For now, let's leave it there. Let's go to the the P final in the y-axis. This will be equal to what? It will be equal to the mass of 1 multiplied by the velocity of 1 final in the y plus the mass of 2 multiplied by the velocity final of 2 in the y. And this will be equal to what? It will be equal to 0.150 multiplied by the final velocity in the y will be equal to what? It will be equal to v final of 1 in the y sine theta plus the mass of 2, which is 0.260 multiplied by the final velocity of 2, which is 0.7 cos or sine rather. This is the y-axis and it is pointing in the negative direction. This will be negative or 0.7 sine theta, which is the theta which is equaling 35 like that. Okay, so these are now the two equations that we are having. Now, we are now going to go back to the conservation of momentum. We know to say initial momentum should be equal to final momentum. So what are we going to do? We're going to say initial momentum in the x is equal to final momentum in the x. Initial momentum in the x is equal to final momentum in the x. And the final momentum, initial momentum in the y rather. Initial momentum in the y should be equal to final momentum in the y like this. So we're going to equal these guys. The initial momentum that we found in the x should be equal to the final momentum that we found in the x-axis. And the initial momentum that we also calculated in the y should be equal to the final momentum that we have calculated in the y-axis in that manner. So let's now plug those things into our equation. Our new equations rather, since it's just like we're coming up with new equations. So let's start with the x-axis. We're going to say the mass of 1 multiplied by the velocity of 1 in the x final in the x plus, or rather cos theta, I forgot the cos theta, v1 final cos theta, of which the theta we don't know it, plus the mass of 2 multiplied by the v final of 2 cos theta also, which is cos 35 in this case, should be equal to the initial momentum that we calculated in the x, and we found this guy as 0.244 like that. Okay, so let's plug in what we know in this case. So we have mass of 1, v1, final in the x, cos theta, plus we have m2, which is 0.26, v final, 0.7 cos 35. This will be equal to 0.244. Okay, so I'm having to punch what I have here, which is 0.26 multiplied by 0.7 cos 35. And this is giving me this guy will be equal to 0.4 or 149 rather. This is equal to 0.244. So I'm going to take this guy to the other side of the equation. Hence, I'm going to have mass of 1, velocity of 1 in the final x cos theta being equal to 0.244 minus 0.149. So this is equal to 0.095 like this. Then what do I have here that I can divide on both sides of the equation? I have m1. Even this side, I divide the m1. I only want to remain with the things that we don't have. So I'm going to have v1 sine on x cos theta will be equal to 0.095 divided by the mass of 1, which is 0.215. And this is giving me 0.63. So we have this equation from the x-axis. We have that equation from the x-axis, and can put the units here if we want, meters per second. Then we now go to the y-axis. We say the initial momentum in the y-axis is equal to final momentum in the y-axis. So I'm going to say P or M1 V1 final in the x sine, or in the y, this is in the y, sine theta minus, since I said the direction of the velocity in the y-axis of port 2 is towards the negative x, the negative y-axis, we are going to depict it as negative in our equation. So it will be minus m2 v2 final in the y sine 35. This will be equal to the initial momentum in the y. And what did we find as initial momentum in the y? We found it negative 0.087. Okay, like this. So we have m1 v1 f in final sine theta minus the value m2, which is 0.26 multiplied by 0.7 sine 35. This will be equal to negative 0.087, which was the initial momentum. So we punch this into our calculator, and we are going to get a value which is equal to 0.26 multiplied by 0.7 sine 35. It's giving me 0.104. So this is 0.104 being equal to negative 0, even this one is negative, being equal to negative 0.087, like this. So if I take this to the other side of the equation, this one will become a positive. That means I'm having m1 v1 final in the y sine theta, and this will be equal to negative 0.087 plus 0.104. So I'm going to have m v1 and just punch quickly. Okay, negative 0.087 plus 0.104. Okay, so I'm getting 0.017, 0.017. I divide both sides by m1 as usual, and this side by m1. I'm getting v1 final in the y sine theta is equal to 0.113. So v1 final in the y sine theta will be equal to 0.113 meters per second, like that. So this is the equation that we are getting in the y-axis. Now we have two equations, both in the x and then the y-axis. So what are we doing next with these two equations? We're now going to bring about our knowledge from vectors. That means we are going to divide the equation 1, which was that one which is on top of the x-axis, into equation 2, which is this guy which we have here. Let me label this as equation 2. And what are we going to have in the end? We are going to have V1 final in the x cos theta being equal to 0.63. This is what we have in equation 1. And we're going to divide this guy into this equation that we have here. Hence, we're going to have V1 V1 final in the x in the y sine theta, which is 0.113 divided by V1 final in the x cos theta, which is equal to 0.63. So the V final and the V final cancel out here. What are remaining? The remaining sine theta cos theta. And even on the right hand side, we have these guys which are going to divide into each other. Okay, so we are going to have sine divided by cos, which will give us tan theta, being equal to, we divide 0.113 over 0.63. This one is going to give us 0.184127. Okay, like this. And we're going to say theta is equal to the tan inverse of 0.184127. And if I plug this into my calculator, I'm getting my theta as 10.43 degrees. So this is the value of the theta that we've been looking for. So the direction of V1 final is 10.43 degrees above the positive x-axis. Now that we've calculated the theta, we can go ahead and plug this theta into one of these equations. So we plug it into the first equation of the x-axis, which is saying V1 final is equal to cos theta, or V1 final cos theta is equal to 0.63. So going to use this one, V1 final cos theta is equal to 0.63. So we're going to divide both sides by cos theta, even here by cos theta. Yes, cos theta is disappearing from the left-hand side of our equation, and we're going to have V1 final being equal to 0.63 divided by cos 10.43. And this is giving us a final answer, which is equal to 0.64 meters per second as the final velocity of ball number 1. So we've calculated both the theta and the final velocity of ball number 1, just like that. Hence, we are done with question B there, and overall we are done with question 1. We are done with the two parts, which is part A and part B. Okay, so stay blessed. Kindly like, share, subscribe to the channel for more of such solutions, and leave a thumbs up. And until next time, stay blessed.